Very good evening to Dr. Imran. We are from Group 5, Multimedia Computing, taking distributed system. And this is our assignment 1 regarding about the Java Bruteforce MD5 password searching. So I'll be introducing my group mates. They are Aina Misha, Awang Zohaimi, Azri, and Muhammad Aiman bin Aziz. And my name is Ebron Abdulingi. I am the leader of this. So these are the task distribution, and since we have 5 string length to do and we have 5 group members, so we'll take one of each. So Misha will be doing the 2 character string length, Azri will do the 3 character string length, Awang will do the 4 character string length, Ayman will be doing 5 characters, and I myself will be doing the 6 character string length.
For this task, we implemented independent searching where each character are split into 5 members and are executed on different computers.
My name is Awang Sohaimi, and today I'm going to present about our program, which is Brute MD5, and I'm going to explain about what's inside the Brute MD5 program. So basically, it has main function, and then some other functions such as usage, branch benchmark, and run crack with progress, and also some other user-defined class called cracker worker, and some other global functions. And now I'm going to elaborate about the main function. So the main function is basically will check whether the user run the program in the correct command, and the use of the use of command as follows, such as we have two usage, which is the benchmark, checking the benchmark by key in the bench with the number of threads, and the second, which is the total amount of time to find the thread. And also another function such as crack, using Java Brute MDI progress with MD5 hash and number of threads. For the benchmark, if every command meets the requirement, it will then get to the thread from the command, and as well as the seconds, which is the elapsed time, and also perform the range benchmark function. And lastly, for the crack mode, same goes with the benchmark. Is every command meets the requirement. Every command that user put it at the first time they run the program, it will then get a thread from command as well as the target number, and then perform run crack with progress function.
Hello, my name is Muhammad Azri, and today I'm going to explain the usage function. So basically, this usage function tells the user to prompt the correct format for the cracker to run properly. So for example, it will ask the number of threads and the hash if there is no string detected.
For this part, I'm going to elaborate about the function called run benchmark. So this batch of code shows the first part of the run benchmark, and this function returns the benchmark for all of the threads with its duration, hashes, and hash per second. And this is good for user who wants to see the comparison between threads without having to configure it manually. However, this requires continuous CPU use, which makes the calculation sometimes inaccurate.
Next, I am going to explain the run crack with progress function. So, firstly, the program will initialize the len start, search start, and search end to search the acquired total value. Then, the program will begin for search candidates and as well as begin execute a service by using the function new work stealing pool. Then, the executor service manages the threads. Inside it, there is a cracker worker function where another user-defined class is called, which will be explained later. For the next part, the program will continue with showing progress log, and for this, we use the scheduled executor service to manage the scheduled threads. The progress log displays the data such as percentage of the progress, number of threads that are done and the estimated time. If the thread is found, the result log will display along with the details such as string threads. If it is not found, the program will display not found message.
So this is the atomic boolean. This particular code is mainly used to optimize and to allow safe
So
thread
now I will be
processing
explaining the
program
cracker
which are
worker class.
executed concurrently.
So this class
Besides
attempts
that,
to find a
the
plain
atomic
text
boolean is
password
also used to
that
stop
when
the
run
program from
through the
rendering when
MD5
the
hashing
password
algorithm
is
or
found.
program, it will produce a specific target hash value, and it works by systematically generating every possible password within a given set of character lengths and comparing the MD5 hash to the target. And to speed this up, the work is split across multiple threads.
These are some functions declared outside the class that also used in crack worker class and in other functions.
Okay, so for the first test, I was in charge of decrypting a 2-character password. The MD5 hash we were given looks like, as you can see, a long string of jumbled letters and numbers, basically unreadable to humans, but our goal was to brute force it and find the original 2-character input. The actual password for this test was 10, and because the search space is so small, the program cracked it almost instantly. That's why you will see the estimation time marked as not applicable, as the result appears faster than the program can even generate a proper estimation time. From the table and graph, you can see that increasing the number of threads does make the process slightly faster, even though the job is tiny. Overall, this test confirms that our MD5 password search tool is working correctly and that the multi-threading is functioning as expected.
For test 2 to 3 character strings, which is tested by me, Azri, it is found that the graph is steadily decreasing where the higher the number of threads, the faster the hash is solved. The 3-character string that was found was PE and a percentage symbol, and the estimation time is not applicable because it is instantly cracked.
Now I'm going to elaborate about the testing tree, which is the testing towards 4-character string. And as we can see here, for the thread 1, we have the elapsed time for like 7.1 at 9 seconds, and then the estimation time based on the log given is 13 seconds. And then the second one goes a little bit higher, which is 7.923, and then it will slope down for the rate of the thread, which is starting for the 4.451 until and then decrease to 3.106 for the 6th thread, and then going on to the 8th thread, which is 2.666 seconds, and lastly for the 10th thread, which is 2.358 seconds. For this one, we got a string of length 4, which is L, V with small letter, and DS.
This is the 5-character string tested by me. As we can see from the graph, thread 1 to 10, there is a significant fluctuate. Starting off from thread 1 to 2, there is a huge dip in elapsed time. Then it gradually increases from thread 2 until thread 8. Finally, from thread 8 to 10, we can see that there is a huge dips in elapsed time, just like thread 1 and 2.
So this is the 6-character string tested by me, and from threads 1 until 10, we have different kinds of elapsed time and estimated time for hashing completion. And from thread 1 thread 2 there's an increase, and then from thread 2 to thread 4 there's a significant or a dramatic drop down to thread 6, and then there's a small rise to thread 8, and then a small drop in thread 10.
So this overall graph shows how long it takes our program to crack passwords of different lengths when we change the number of threads. Each line represents a different password length from 2 characters up to 6 characters. As you can see, the 2 and 3 character passwords finish almost instantly and don't really change how much no matter how many threads we use, as the search space is tiny, so it's fast either way. For 4-character passwords, there's a noticeable drop in time as we increase the number of threads, especially when jumping from 2 threads to 4 threads. This is where multi-threading actually starts to make a difference. But once we hit 5 and 6 characters, the time stays almost the same across all thread counts. This suggests that our current implementation hits a limit, either from how the workload is divided or from overhead in the system, and adding more threads doesn't speed it up further. Overall, the graph highlights where multi-threading helps and where it doesn't, and it gives us a clearer idea of how the program scales as passwords get longer.
So that is all from us, from Group 5. Thank you, Dr. Imran, for watching, and we hope that you would have a blessed and productive day ahead. Thank you.